This presentation is on statistical learning in thermoacoustics. The work was done by me, Francesco Garita, with a precious contribution of Hans Yu and Ushnish Sengupta, and under the supervision of Professor Matthew Juniper. Thermoacoustic oscillations arise because of the interaction between acoustic waves inside the duct or a combustion chamber and heat release rate fluctuations at the flame. The reason why they are relevant is because the noise and vibrations that appear as a consequence of this interaction can have catastrophic consequences. This has been a relevant problem in the design of jet and rocket engines for a very long time. The fundamental challenge is the very high sensitivity of the growth rate of these oscillations to design parameters, which significantly amplifies small systematic errors present in our models. So we need our models to be as accurate as possible in order to be useful for design. In order to build highly accurate models, we take a qualitative model and use statistical techniques to make it quantitatively accurate using lots of data. We carry out experiments on a simple thermoacoustic system made up of a 1 meter long vertical tube with a diameter of less than 5 centimeters. We then put an electric heater inside it. The heater is made up of 2 ceramic rings wrapped around by many thin filaments and held in place by 2 prongs. This system is known as Ricky tube and is the simplest thermoacoustic system you can imagine. In spite of its simplicity, it contains much of the relevant physics present in a real jet engine. For our experiments, in addition to the heater, we use 8 thermocouples to measure the centerline temperature and a thermocouple to measure the ambient temperature. Simultaneous measurements are taken every 7 seconds. By fully automating the rig, we managed to collect more than 1 million data points. In our experiment, we changed the heater power in steps of 10 watts, going from 10 watts up to 180 watts, and we investigate 10 different heater positions. The first thing we do is model the buoyancy-driven flow. To do so, we use an unsteady conjugate heat transfer model that consists of 2 partial differential equations, one for the gas and one for the solid, and a momentum integral equation. These 3 equations are all coupled between each other and depend on 3 parameters: 2 Nusselt numbers that characterize the heat transfer from the gas to the wall and from the wall to the surrounding air, and an inverted loss coefficient that quantifies the pressure loss that occurs across the heater. The model assimilates temperature measurements every 7 seconds, and when it does so, both state and parameters get updated. We perform data assimilation using the ensemble Kalman filter, which in the simplest case works in the following way. We start from a prior distribution based on our knowledge, for example a Gaussian distribution, and then we take n samples where n represents our ensemble size. Then each member of the ensemble gets transported to the new state through our model M. Notice that the corresponding new distribution is non-Gaussian if the model is non-linear, like in our case. We then approximate this new distribution with a Gaussian distribution. The estimate of this state, which we call the predicted state, represents the knowledge we have purely based on our model. Next, we build a Gaussian distribution around the temperature measured by the thermocouple based on a standard deviation that comes from experience, for example plus minus 2 Kelvin. Our problem now becomes finding a way to combine these 2 pieces of information to obtain the best possible estimate of the true state. To do so, we use Bayes' rule. By applying Bayes' rule, we obtain a new estimate of our state that we can use as prior for our next iteration. This procedure can be used to estimate not only the state but also the parameters. So the model simulates the experiment dynamics, and every time experimental observations become available, it updates state and parameters at the same time. The state, in our case, coincides with a long vector of gas and solid temperatures to which we append the three parameters of our model. As far as the ensemble common filter is concerned, we find that using an ensemble made up of 30 members is sufficient to obtain accurate results. The ensemble members represent different simulations that run in parallel and interact between each other in the way explained so far. Here are two snapshots of the assimilated gas temperature profiles and the corresponding measurements for each of the 10 heater positions. The left figure refers to low powers and the right figure to high powers. From our model, we can infer the inlet flow speed, which increases with the heater power, reaching a plateau at high powers. Notice that the value of this quantity are rather small, around 0.5 meters per second. This means that the Mach number is close to zero, and hence it is reasonable to assume negligible mean flow speed when developing the acoustic model. Temperatures and inlet bulk speed are used to build the acoustic and thermoacoustic models. The experiments described so far do not include only thermocouples and electric heater. In fact, the full experiment is much more involved because it includes also a loudspeaker placed at the bottom of the tube which provides an acoustic ping every 7 seconds. In addition to the loudspeaker, a set of 6 probe microphones is installed on the rig, by means of which we measure the pressure inside the tube continuously at a frequency of 10,000 Hz. This picture shows one of the acoustic pings we provide through the loudspeaker and the following decay as seen by the 6 microphones. We use the microphones to measure decay rate and frequency of the oscillations in the decaying part of the signals. In the top right corner, you can also see the magnitudes of the normalized 6 complex pressures and the corresponding pressure eigenmode, which, for a tube open at both ends, has a pressure antinode in the middle of the tube. The values of the complex pressures are used in the multi-microphone method to compute the downstream reflection coefficient, which changes when the temperature changes. Here you can see decay rate and frequency of the oscillations inside our tube at different heater positions as function of time, the bottom axis, or as function of the heater power, the grey bars at the bottom. The goal is to build a reduced order model that is able to accurately predict all these observations. The second step for us is the modeling of the fast timescale, the acoustic timescale. For this, we use a network model made up of 50 acoustic elements. In each of these elements, we solve the Euler equations in the assumption of no mean flow because, as we saw before, the Mach number is close to zero. The solution of these equations in each element is obtained by performing a Riemann decomposition, which results in an F wave traveling downstream and a G wave traveling upstream. Different elements correspond to different waves. We then connect adjacent elements by specifying the jump conditions at the interface between two elements. For an empty tube, the jump conditions represent viscous and thermal acoustic losses in the boundary layer, which are obviously distributed losses, but which we model as concentrated losses. Notice that the two coefficients highlighted in red are fully known because they are only function of geometry, fluid properties, and oscillation frequency, which we know. So the question is, since we know the model parameters for the empty tube case, how do we use this model? Well, we first perform some experiments in the empty tube case, and then we use these experiments to infer the boundary conditions, the only unknown of our problem. This translates to inferring the reflection coefficients at the two ends. In the cold flow experiments, we assume the two ends to be identical and therefore characterized by the same reflection coefficients. In the hot flow experiments, the reflection coefficients are instead computed using the multi-microphone method. Now we know everything about our empty tube. What do we do next? The next step is to introduce the electric heater in our acoustic model. This translates to adding an additional acoustic element at the heater position with the corresponding jump conditions. The way in which the viscous and thermal acoustic losses across the heater are modeled is by using a model made up of 4 parameters highlighted in red. Unlike before, these 4 parameters are unknown to us, so we need to infer them from experiments. Likewise, we model the 8 thermocouples inside the tube by adding 8 additional acoustic elements. We assume the thermocouples to be identical. The model for the thermocouples is simpler compared to that for the heater because it does not involve any time delay. So now we have a full acoustic model that relies on 6 parameters in total, which we need to infer. To infer these parameters, we perform lots of new experiments with the heater inside the tube switched off, placed at different locations, with and without thermocouples. For each experiment, we measure temperatures, decay rates, and frequencies. The result of this process is shown in these figures, where you can see a comparison between experiments and modeled predictions of the decay rates in the top figures and of the frequencies in the bottom figures, and this for different heater positions. The left figures represent the case of no thermocouples, whereas in the right figures the thermocouples are present. You can see the additional drag due to the thermocouples in the top right figure, where the curve is shifted downwards compared to the top left figure. The model parameters are inferred by simple regression and are reported in the figure captions. As you can see, the agreement between experiments and the physics-based model predictions is very good. Can we actually use a better inference method than simple regression and quantify the uncertainty in the parameters? Yes, we can, and for this purpose we use the Markov chain Monte Carlo, which, in the simplest case, works in the following way. We first define a prior distribution of the parameter theta, for example a uniform distribution if our a priori knowledge is limited. Then we denote by psi-exp the experimental observation of the state, which in our case is the growth rate and frequency of the oscillations. Next, we pick a random parameter from this distribution, which we call theta 0. Then we introduce a proposal distribution, for example a Gaussian distribution, and we center it around theta 0. We randomly sample a new parameter from this distribution, which we call theta star. Now we compute the acceptance ratio R, defined as the ratio between the posterior values with theta star and theta 0. Using Bayes' theorem, this translates to the product between the likelihood ratios and the prior ratios. The acceptance ratio tells us whether the new sampled parameter, theta star, is more or less likely to be observed than theta 0, given our data. Suppose that the acceptance ratio is much smaller than 1. This means that the posterior density is much smaller with the new parameter, so the algorithm rejects the value of theta star and samples a new parameter. With the new theta star, we recompute the acceptance ratio. If the acceptance ratio is greater than 1, then the algorithm accepts the proposed parameter, theta star, and uses it for the next iteration. For the next iteration, we repeat the steps shown before by centering the proposal distribution around theta 1. To summarize, the algorithm always accepts parameter values that increase the posterior density, but only sometimes accepts downward values. The fact that it does not always reject downward values preserves the stochastic nature of the algorithm. So the Markov chain Monte Carlo essentially constructs a biased random walk that explores the target posterior distribution in the parameter space. Typically, you run several Markov chains in parallel, starting from different initial parameters. The chains are all independent because they are Markovian, which means that each state in the chain depends uniquely on the state at the previous iteration. In practice, if you let the chains run for long enough, they will converge to the desired posterior distribution. Here you can see how the posterior distribution looks like for some of the acoustic parameters. The MCMC is a more powerful tool than the ensemble Kalman filter because it does not assume Gaussian posteriors. Therefore, it can explore any possible nonlinearity or multimodality present in the posterior, as you can see in these examples. Once we compute the uncertainty interparameter space, we can propagate this uncertainty to the state through our model using the standard Monte Carlo method, for example. The result of this process is shown in these figures, where you can now see the uncertainty of our model represented by 95% confidence intervals. These results are analogous to the ones shown before, but are much more robust because we know the uncertainty. Moreover, notice that, unlike before, here we are using only 27% of the data as training set, highlighted in blue. Yet, the model is able to extrapolate very accurately beyond the training range because it is physics-based. When we switch on the heater, we perform experiments again at 10 different heater positions, and we investigate heater powers up to 180 watts in the way described earlier. With these experiments, we train our thermoacoustic models and infer their parameters and uncertainty. In this study, we test 3 different thermoacoustic models. The first one is the popular n-tau model, with n and tau both constant. In the second one, we assume the time delay to be inversely proportional to the inlet bulk speed, as suggested by Lighthill. In the third model, we instead assume tau to vary as an affine function of the heater position, thus introducing one additional parameter. For the hot flow experiments, we want to use again only a very small training set to see whether the model can extrapolate well. If we look at the model predictions when the normalized heater position is 0.10, we can see that the n-tau model does a particularly bad job. Indeed, the predicted decay rate at high powers is several standard deviations away from the experiments. Even if we use all the data we have as training set, it is not possible to find a unique n and a unique tau that describe all the data well. This means that the model is inadequate. The n-tau model provides accurate results only if the heater position inside the tube does not change. Every time the heater position changes, the model needs to be recalibrated. The same holds for model 2, where the time delay is assumed to be inversely proportional to the inlet bulk speed. What happens when we introduce a bit of flexibility in our model? Well, if we assume that the time delay is an affine function of the heater position, as Model 3 does, then the results improve significantly. Here I show the results only at the heater positions most difficult to predict. Even though the model has never seen this data, it can extrapolate fairly accurately, despite the uncertainty in the rightmost figure being relatively large. Here you can see a quantitative comparison between the 3 models. For each of them, we compute the average log likelihood per data point and the root mean square error of the growth rate and of the frequency. As you can see, Model 3 is characterized by a less negative log likelihood as well as by a significantly smaller RMSE of the growth rate, proving that Model 3 performs much better than the other 2 models. This brings me to the conclusions of this work. The study we did lies at the boundary between physics and data science. We based our analysis on physical principles as much as possible and let the data suggest a closure relationship when it becomes too difficult to identify the physical mechanisms. We saw that a qualitative model can be turned into a quantitative model if it's based on physical principles. And we also saw that many commonly used thermoacoustic models are quantitatively accurate only when limiting them to specific configurations. Finally, the probabilistic approach we used can be applied to a wide variety of engineering problems for which the main mechanisms are known so as to evaluate adequacy, accuracy, and uncertainty of the tested models. A preliminary version of this work has been published on the Journal of Engineering for Gas Turbines and Power, and the bulk of the work has been recently submitted to the Journal of Sound and Vibration. To conclude, here you can see the conferences where this work has been presented. Thank you very much.